hydraulic engineer from the Monroe County Conservation District, which you guys probably all have worked with in the past when you bring in your NPS permits. And we'll let you take it away.
Okay, thank you, Lori. Okay, so our last speaker talked about soil testing and all the fun and maybe some of the challenges that occur on our sites because of soil testing. Another thing so what we see and what we're seeing a lot more here is not only, I know if anybody does work in Monroe, we do have issues related to soils here. Most of the time it's poor infiltration rates that are kind of marginal. The other thing that we've been finding out lately is after the sites and the basins and the facilities are built, sometimes they're not draining. Part of the reason why we're seeing that is the soil testing may be done to a certain level, like down to that 2 feet below the limiting zone, but there's a further deeper restrictive layer that may be stopping the water from continuing to filter down in. So as we talked about in the last seminar, or in the last speaker, these issues related to soils, the managed release concept is something to kind of bridge that gap. It's also something that could be used on these sites where you do have these marginal rates, or even not good rates at all, and where you have some limiting zone issues which you're trying to deal with on your projects. Just a show of hands, how many people have designed an MRC so far? Okay, so maybe about 10%. So okay, good. This will be a good refresher for everybody, or to let everybody know. So, let's see if I know how to work this. Okay, so what are we going to talk about today? What is the MRC, Managed Release Concept? How do we justify when we should use it? Okay, what are the requirements we need to do? There's different system components that make up the MRC. We'll talk about each of those and we'll kind of walk you through from the bottom to the top what those pieces are. The benefits, how you can claim it for water quality, volume. Okay, there is a rate component that could be a part of it as well that you could take advantage of. The design criteria, we'll walk through those steps of what the main criteria is to design these systems. How do we report it on both the new forms and on the old forms, okay? And we'll do an example. I think we're going to have some time to do that example as well. So let's go, what is it? And where do you find information about it? So it's basically a new alternative PCSM BMP. To get to it and the information about it, if you go on the DEP website, MPDS area, you go to the alternative BMP list, you go all the way to the end of that list, and you'll see the managed release concept. And there's 4 pieces that are part of this MRC, or 4 different documents. The first one is the design criteria, which is what we're going to talk about and walk through that today. A frequently asked question report is in there as well. A couple design examples, 3 different design examples, both an above ground and an underground system. And then what's called the MRC design summary sheet, which is basically the summary of all of your calculations that gets attached to your applications, okay? And as we talked about, this BMP bridges the gap basically between volume reduction and volume management. If you look at 102.8G2, it says that you will manage the volume created by your project for that 2-year storm, okay? Most people manage that volume through infiltration. This is an option to manage that volume through management of the system as opposed to infiltration when you have problematic conditions for that infiltration. Okay? First thing you have to do is prove that the infiltration on your project is not feasible. What you use, this basically meets the volume requirement when you meet it with all of the requirements. It can also possibly be used to meet your water quality requirements as well, if it's a vegetative system. The design is similar to a rain garden in that case. Can be above ground or in ground, under pavement. Okay, you could use storage chambers with this thing to get the volume. And you could also incorporate this into your larger rate control basins as well. Okay? So the first thing you need to do is you have to justify why you can't infiltrate. Okay? And that means you do a thorough pre-development site characterization. And there's requirements in the MRC design criteria of what that is. Basically, it's for areas where infiltration is extremely limited. They put the limit at 0.2 inches per hour, okay, which is a little better than the 0.1 that's in the BMP manual now. So it's a little, I think they're starting to realize there's some issues with the 0.1 inches per hour and how big those systems get and how long it takes to drain. Infiltration's not feasible through the limiting zone issues related to high water table, shallow limiting zones, things of that nature, okay? Infiltration is undesirable. We have sinkholes, karst issues. This is a system that could be used in those cases. Usually in those cases it's lined, okay? You have to show that the structural and non-structural BMPs on your site have been maximized to the extent practical. So if there are those non-structural things that you can put in to basically help hit those volume requirements and water quality requirements, you need to show that you've maximized those as much as practical. Downstream path should remain stable below one of these systems. That usually is not a problem because the reductions that you have to do to meet the design requirements are basically really dropping down the rates of your discharge in these situations. The requirements are that the calculations are performed and stamped by a PE, okay? As far as soil testing goes on the site, you would need to do a minimum of 4 tests and tests every 40,000 square feet of area. So you need to basically pepper your site all over with tests to show that not only is the soil not feasible in the area where you want to put your facility, but you do not have other options to redesign or relocate your BMPs to other areas which you could potentially meet the infiltration requirement in that case. So if you have large site restoration areas, okay, those can be taken out of the testing. Okay, so if you have a 20-acre, power line project in a transformer area, or a transformer yard, you wouldn't have to test the whole power line area to show that, okay? And you want to test in the most accommodating soil horizon based on a deep hole test. And I think this gets back to what we were talking about earlier, is you need to take those tests beyond just the first layer. You might have these good limiting zones, and you could have no issues related to limiting zones, but you could have issues related to the rate of infiltration. So you want to look at these deep hole, you want to do a deep hole test, see if there's an underlying zone that may be more conducive to infiltration in that case. So, okay, so the review of these, basically DEP reviews them unless it's been delegated to the conservation district. Here in Monroe, I think all of the delegated districts in the Northeast region are all delegated to review these because we have the engineers and the PEs on staff. In non-delegated districts, DEP will review these if they meet any of these criteria, okay? Drainage area over 3 acres, impervious to the MRC over 1.5 acres. Project impervious increase over 10 acres. That 10 acres includes gravel areas as well. Any impaired waters for siltation and flow attenuation. And we're going to be talking a lot more about impaired waters this afternoon when we go through a lot of the new paperwork and everything with the new permits. So if there's any deviations from the design standards, a general permit, a general NPDES permit would become an individual MPDS permit, okay? So it's important, if you want to keep your project as a general permit, that you meet the design standards that we're going to go over today. So this is the general concept of an MRC and how it works. We're going to basically walk through each one of these components, what they do, how they work in the system, okay? We'll start from the bottom up, basically. So the first two, at the base of the system is a perforated under drain, okay? So that sits on the bottom of these systems. Recommended 24-inch limiting zone. It can be less than that. If you're 12 inches, you're okay. If you're under 12 inches to your limiting zone with the bottom of this system, you need to put a liner in the bottom of the system. There's no separation required above bedrock. So these could be set on bedrock, again with the use of a liner, okay? Under drain with a gravel envelope. So at the bottom of this system is the under drain. It's in a gravel envelope. The gravel envelope and the under drain are sized for the 110 gallons a minute per linear foot of pipe. I'm not sure if that's a 4-inch pipe or what, but it's not a lot. So under drain on the bottom of the system. So what happens is the water filters through the soil component, and this is in the case of an above ground. In the case of a below ground, it would go through the gravel or other medium, hits the under drain, and then is funneled out of the system through the under drain. Okay, it discharges to an upturned elbow and that's the control structure for the smaller storms. So the upturned elbow is the control structure. It's set at the IWS depth, and we'll talk about the IWS next. And the storm that it controls and what the design of that elbow is designed for is the 1.2-inch 2-hour storm outflow, and the design discharge is 0.01 CFS per impervious acre. And we're going to go through how you calculate that in a minute. And this discharge is considered volume that is permanently removed. On the new plan, on the new forms, on the MRC design summary sheet, you need to report that value. That's the volume permanently removed. How we've seen these control structures done, you end up with some pretty small orifice in the under drain to control the outflow. What we've basically seen is people bring the under drain into the box, turn it up, cap the top, and then drill an orifice in the upturned pipe to basically use that as the control structure and to kind of keep that from getting clogged with debris and other things. So that's what we've seen to date on that. And that's usually set at the top of this internal water surface. So the internal water surface is the first minimum 1-foot depth of soil directly above the under drain, okay? So that is soil media. More likely it's going to be soil media mixed on your site because of the soils aren't the best that you're dealing with. It's a minimum 1 foot of depth above the under drain or the first outlet, which is that upturned elbow. The maximum depth of that IWS can be up to 4 feet, okay? If that IWS is made of soil, you assume a 30% void ratio in that soil. In the case of the first foot or half of that IWS, so whatever you're claiming in your system as the internal water surface, half of that internal water surface is assumed to be saturated for the point of your routing, excuse me, for the point of your routing calculations. So if you have a 1 foot IWS, that first foot of soil, instead of using 30% voids in your routing and in calculating your storage in that system, you use 15. That's usually the easiest way to do it, okay? What the IWS does is it performs the water quality function of the system. So what's happening there is basically that's the filtering medium to filter and give you the water quality component of the system. okay? You're going to have a very slow release rate coming out of that IWS, okay? That's to promote the ET component, the evapotranspiration component, okay? And then half of the IWS storage, or that number we just talked about with the 15% voids, is considered that volume that's permanently removed, okay? And we'll get to some of those calculations as well. So as we move up here, so above the IWS and including the IWS is the total soil depth, or what's called the media depth, okay? Again, that's a soil with a suitable infiltration rate, okay? It's a minimum of 2 feet of depth, so you have a 1 foot IWS and a 1 foot additional soil that make up the media depth. That area above the IWS, you can claim the full 30% void ratio for routing. So in your routing calculations, you're assuming that that soil above the IWS is dry, okay? And you get to use the whole 30% in that case, okay? Again, those soils are promoting the ET and providing the water quality function of the system. So then above the soil is what's called the ponding depth. This is the open water, okay? And again, we're talking about an above ground system here. But again, the ponding depth is determined so that the 2-year 24-hour storm takes 72 hours to drain out of the ponding depth. You don't have to drain all the soil in 72 hours. You need to drain the open water in 72 hours in a 2-year storm, okay? So the only water left at the end of that 72 hours is all contained in the soil. And again, for a vegetated system, 75% of the surface on the top has to be vegetated, okay? And then you have an overflow device, which basically handles anything over and above a 2-year storm, okay? So if you think about how this works, the water comes in, it basically soaks into the soil. It's slowly released out of the underdrain, or if you have a small amount of infiltration, you could take credit for that infiltration rate happening during the storm. It's slowly trickled out through the underdrain, okay, till it gets to the point where there's only 1 foot of water left in the system below, and that's either through ET or through infiltration into the soil that last foot is taken out. So what you're basically doing in the concept of this is you're mimicking the groundwater flow basically into the streams by saying, I'm going to give this slow discharge over time, and that's how the volume is being managed as opposed to an infiltration system. So the benefits, so if you design your MRC in accordance with the design standards above ground or below ground, it'll meet your volume control requirement for the area that's contributing to that MRC, okay? If you have a vegetative MRC, above ground system, vegetation, internal water surface, all those components we just talked about, that will meet the volume and water quality component for that area that's contributing to it, okay? So if you have a couple variations, if you have an underground MRC that goes through porous pavements, again, an underground system really doesn't have an internal water surface. You can, if you want, if you have good soils below the underdrain that will still infiltrate, you can credit up to 2 feet of those soils underneath the underdrain and say that's part of the system, that's an IWS, and the infiltration that goes associated with that can be taken into account in your system design. You would need to show that through your test pits and your soil testing that material underneath the underdrain is still able to infiltrate. Again, the underdrain is the control structure that goes that handles anything above, takes it into your main control structure. Porous pavement, if you're going through the porous pavement or you're using the porous pavement to handle your water quality component, that would have to be designed and maintained to meet the water quality requirements of the porous pave, okay? In this case, if you have a system that does not provide water quality function, you would just basically, when you did your water quality analysis, you would ignore the MRC for the purpose of calculating your water quality requirements. In the case of an underground MRC, let's say with storage chambers, you usually don't have an IWS, that's a purely gravel system, that's still fine. You would need to show adequate pre and post treatment for water quality coming into that system and going out of that system if additional water quality was needed. Again, in that case, you would not use the MRC in the water quality calculations. You would just show the treatment that's happening before and or after the system, okay? Wrong way. Going the wrong way. Okay, figuring out the clicker. Okay, so here's the design criteria. So the first design criteria is that the release rate for the 1.2 inch 2-hour storm should not exceed 0.01 CFS per acre from the equivalent impervious area, okay? So you need to calculate, that will determine what we call the volume removed that we talked about before, okay? And we'll get into that again. The peak flow from the 2-year 24-hour storm has to be taken back to the 1-year pre-development storm, okay? That determines what are called the geomorphic volume and the volume that's being managed, okay? And the third criteria is the ponding area should drain within 72 hours for that 2-year storm. So what that's going to do is that's going to drive the size of the system, because in the case of the 2-year storm, the only outflow that's occurring in that 2-year storm is going out of the underdrain. So it's going to be a very small rate. So you can't build a lot of ponded area on this system, otherwise you're not going to be able to meet the 72-hour drain time. So that 72-hour drain time is going to drive more of the footprint of the system that you need to meet the requirements. Okay, is everybody, maybe New Jersey DEP 2-hour 1.2 inch storm, is anybody familiar with that? Yes, no? Anybody doing work in New Jersey? No? Okay, so the 1.2 2-hour storm is basically the New Jersey DEP storm for water quality. This is hydroflow, and this is a 24-hour storm, the red line. The green line is the 2-year storm. If you have hydroflow, it's just New Jersey. You go to New Jersey DEP 2-hour, and you'll get the rainfall for that. If you need to recreate it, we've given you the distribution here, this last column. If you need to recreate it in your system, it's a 1.25 inch storm, but it's pretty close, and it's been, again, it's been used. This is a pretty standard storm in New Jersey. That's what it's based on. So if you need to recreate it, and if you have a different model, this is the numbers to recreate the storm. So with this 1.2 2-hour storm, basically you need to determine the allowable discharge from this underdrain. So what's going to be that controlling discharge? So if you look at, it's going to be 0.01 CFS per acre from what's called the equivalent impervious area. So how do you get the equivalent impervious area? Well, you get your calculation, you get your watershed to your MRC, you run the hydrograph for the 1.2 inch 2-hour storm, and you get the total volume in the hydrograph. You take that total volume in the hydrograph, in this case in cubic feet, divide it by 0.083, multiply it by acreage for the conversion, and you will get what's called the equivalent impervious area, okay? You take that equivalent impervious area, you multiply it by 0.01, that gives you the discharge that should occur out of the underdrain upturned elbow, okay? You route the storm through the system, again, assuming 15% voids in the internal water surface and 30% in any of the soil that's above that. And the total and the volume that's permanently removed from the system is whatever's in the IWS plus the discharge volume that occurs through the underdrain, okay? And we have an example, we'll show you that. Wrong way again. Okay, then the other point is the geomorphic volume. So you take your 2-year, 24-hour storm, basically reduce it to the 1-year pre-development rate. Then the volume managed in that case is all of the volume that's being discharged through the underdrain. So if you have an overflow device, basically anything that's below the overflow device or below the first outlet over and above the underdrain, that water surface down would be the volume that you could claim, because that's all going to go out the underdrain, right? Then the geomorphic volume is another one that's reported, which is just basically the difference. The volume managed based on the 2-year storm minus the volume permanently removed based on the 1.2-inch storm, okay? So how do you report all these numbers after you do this design? Well, there's the MRC design summary sheet. It could also be, it also is reported on the new PCSM Module 2. And in the case where you can still use worksheets 4 and 5, even with the new system, it could be reported on worksheet 5 as well. And we'll show you where to put each one of these. So this is the MRC design summary sheet. The first page is just basically some general information, name, applicant, the BMP type, the name of the surface water, is the surface water impaired, just some yes, no questions, criteria used in the design. Then we get into the details, and here it'll give you the design standards as well, so that you could check that your numbers are meeting the design standards here. And again, some information about the system, void space, media depth, bypass elevation, bottom elevations, under drain sizes, all of that stuff here. Basically a summary of your system. At the bottom of that is the 3 numbers that we just talked about. Basically, if you have a rate control system, you could put the rate control through the MRC here as well. But basically, volume managed by the BMP, volume permanently removed, and the geomorphic volume. So that's where those 3 values end up going into this summary sheet. This summary sheet gets attached to your application, whether you're using the new spreadsheets or you're using the old worksheets. This gets attached. On Module 2, PCSM Module 2, right at the bottom, manage release credits, and you attach the design summary right there. And the volume managed, again, from that 2-year storm is what's reported in this case, okay? That's just plugged in and it goes into the calculations for the new spreadsheets. If you're using worksheet 5, where you would report that would be at the bottom of worksheets 5 under other, okay? Again, volume removed, that's the 1.2-inch storm. The geomorphic volume is that difference, so that when you take A plus B, it adds to here, okay? So here's a quick design example, kind of show you how to use this. So let's say we have a 2.8 acre site, 80% of the site is impervious, 20% is grass, and we need to do an MRC to basically handle this situation. So here's our worksheet 4, basically calculating our required volume reduction, and we come up with our volume reduction of 12,829, okay? This is the New Jersey, so we run the New Jersey DEP 2-hour storm, okay? And we see that the runoff area in this case, 121,968, that's the 2.8 acres. The runoff volume that's generated from that storm is 6,634 cubic feet. So we take 6,634 feet, divide it by the 0.0833 times the 43,560, we get 1.83 acres. So what that 1.83 acres is, it's saying a 1.83 acre site, all impervious, okay, will generate the same amount of runoff as this site, okay, and it'll equate to about a 1-inch runoff event from the 1.2-inch rainfall event, okay. So we get 1.83 acres, we take 0.01 times 1.83, we get 0.0183, we're going to use 0.02 CFS. Round it to 2 digits, don't round it out to 16 significant digits. Take advantage of the rounding. So here's an example of how that kind of equates that we just talked about. So here is a 1.83 acre site, 100% impervious. And you could see the rainfall depth in this case is 1.03 inches, a little bit over 1 inch. And the runoff volume is 6873. So it's close, it's not going to be exact, but you know, we got 6634 cubic feet from our storm from our site. In the equivalent site, we got 6873, about a 3% difference, okay? So it's close. So that'll just show you, you kind of get the same amount of volume. So if we look at our system, and we're going to say our system, the bottom of our system is at elevation 100, okay? And our system's going to have that under drain sitting at elevation 100. We're going to have a 1 foot deep internal water surface, and the volume in that 1 foot deep is going to be based on 15% voids. So the top of the IWS is at elevation 101. We have another foot of soil media above the IWS. That 1 foot of soil is going to be based on 30% void ratio. So that the top of the soil is elevation 102. And then we're going to have 2 feet of open ponding depth above that. So we'll call the top of the pond 104, okay? So just taking a rough number here, if we say a target discharge of 0.02 CFS, we say a head value of about 2 feet to the top of the soil. We need a 1-inch orifice in the under drain at elevation 101 at the top of the IWS, okay? So here's our routing with that case. So we look at this, our inflow in is 586. Our outflow, which is all through the under drain and the 1-inch orifice, is 0.02. And the volume associated through the under drain is 3796. From our storage calculations, at elevation 101, we have a storage volume of 2,600. And that's based again on the 15% void ratio in that 1 foot section. So if we want to look at the volume that's permanently removed in this case, the volume that's removed is the 2,600, which comes from here, plus the 3796, which is the volume that went out through the under drain, for 6396 cubic feet. So that is our volume permanently removed, okay? So now we look at the 2-year storm. So if we look at the 2-year storm, we need to size the 2-year outflow based on a 1-year pre-development. And in our case, our 1-year pre-development will be 1.8 CFS, okay? So easiest way to do this, or a hint to help get to the answer quicker, when you build your system and you get your storage value, set your first orifice out of the basin at the volume which equals your required volume from worksheet 4, okay? So in our case, our volume was 12,829. So I look at the routing from here, and I look at my volume, and where 12,829 ends up, and that ends up at about 102.35, okay, in this case. So the 72-hour dewatering time in that amount will dictate the size and the footprint of the system. So you may even want to run this design first with some ideas, and then run the 1.2 after you get the sizing and the aerial point correct. So if we look at worksheet 4, like we said, we got about 12,900 cubic feet we need to manage. At 12,900, we set the orifice at 102.35. So if I want to look at how much ponding area or how much volume should be between 102.35, which is the first orifice, and 102, which is the top of the soil, that's that open ponding depth again, that amount of storage should be 0.02, 3,600 for conversions. Under drain discharge rate conversion times 72 is roughly 5,184 cubic feet or less. Needs to be the numbers between 102, the top of the soil, and 102.35 to roughly meet that 72-hour requirement. Okay, so that'll give you an idea. Usually what happens is if you size these too small and too deep, you're not going to meet the 72-hour requirement, okay? Because the under drain is just not going to be able to drain out that open ponded area quick enough to meet the 72 hours. So that's what will drive the size of the system to get that ponding depth down. So in this case, here's our 2-year run. So you can see our inflow in was 9.19. Our outflow out is